In this lecture, we're going to learn about what it means to be an orientable manifold. Let's recall some definitions. X is a smooth manifold. I will drop the word smooth from this point on. X is a smooth manifold if and only if there is a collection of maps. It could be a finite collection, it could be an infinite collection, where each, and let's emphasize this is an n-dimensional manifold. So if it's an n-dimensional manifold, then these maps f lambda, or maybe we sometimes call them phi, does not matter what you call them, they map Rn into X. Also, as was indicated on the homework problem, it is useful to allow more flexibility. It does not necessarily have to be Rn itself. It could be an open subset of Rn. It's just that it's more convenient to just assume it's Rn. But in the definition, you could give more flexibility and just use this as an open subset of Rn. But anyway, these are mapping Rn into X, and this maps Rn homeomorphically onto an open subset. Let's call that open subset X subscript lambda. So that's an open subset of X. So that the union of all of those open sets, they give you X. So we call these, of course, each of these are called charts. And this entire collection is called an atlas. And the idea is that the charts, they map copies of Rn onto open sets, but the open sets completely exhaust and they give you everything. That's why we call it an atlas, because everything is covered. And we have the condition that if you do phi lambda composed phi mu, then this composition is a smooth function. So let me kind of rewrite this like this. So let's say we have some kind of smooth manifold, and we have Rn being mapped by phi lambda to some region over here, and then we have another copy of Rn. Yeah, I mean, in this picture, of course, it's R2, but more generally, it's Rn. This is being mapped to phi mu, and these overlap. So those are the image sets, and these overlap. Now, if they do not overlap, there's nothing to check, but they overlap in some open set, because the intersection of two open sets is an open set. So they overlap in an open set, and if you pull back that open set, you get an open set in Rn, and then you get another open set in Rn. And then this composition, when you do phi lambda and then you compose it with the inverse, in general, it's not going to be defined on Rn. It's going to be defined on the smaller open subset of Rn. And you can write out what that open set is, but we often do not really care so much what it is. And I'm just going to write that this is, I'm going to use the following notation. It's a notation that is sometimes used in algebraic geometry. You're going to write this as, it's a mapping from Rn, and you're going to use a broken line into Rn. And all that means is, that means that this is not necessarily defined on all of Rn. It's defined on an open subset of Rn, and it maps this to another open subset of Rn. Actually, it's a homeomorphism between two open subsets of Rn. So we just use a broken line to sort of indicate that, with the understanding it's not necessarily globally defined on Rn. So this homeomorphism is smooth. So smooth will just mean that the partial derivatives of all of the component functions exist, and you can take as many partial derivatives as you want. So that is the definition of what it means to be a smooth manifold, which we will just call manifold. Now, the idea here is when you are mapping a chart onto an open subset of your manifold, there's a question of which side do you see. So this is basically the question of when you map a chart. So maybe when you map Rn onto the manifold, which side do you see? So of course, we're being vague here, but we're trying to develop an intuition for what we're about to do. You see, you're in this picture, we're taking the square, and imagine you're lifting the square and you're just mapping it to that region. But another thing you can do is you can pick up that square, and before you put it down, you kind of flip it over and it points the other way. So the side that is facing you, when you map it onto the torus, let's say it's the torus, it's pointing in the other side. Maybe it's easier to use a sphere. So maybe I should take this down and do it with a sphere. It might be a little bit easier to see this with a sphere. So you have your sphere, and you can talk about the inside of a sphere and the outside of the sphere. And when you map a copy of R2 homeomorphically to some open subset of the sphere, the side that is facing you, when you copy and paste it over here, is the side that is facing you, facing, do you see the outside of it, or do you see the inside of it? In other words, imagine taking this piece of paper, this flat sheet of paper, and when you move it over, you sort of flip it over first. So maybe you kind of flip it over so that the side is now facing the other way, and then you put it over. So that is the question that we're trying to ask. Now, one way you can always flip it over is actually very simple. If this function is f, so this is a function from R2 to the sphere, one way you can flip it over is you can define a new function from R2 to the sphere. And a very easy way how you can change the orientation is this new function is defined by using the old function, but you swap the roles of x and y. And as you know from a very basic math course, that if you interchange x and y, that has the effect of doing a reflection through the diagonal. Right? If you have a graph and you interchange the roles of x and y, you're just doing a reflection through the diagonal line. So that would mean that before, so let's say the original f maps this to that piece. Imagine that you drew the diagonal down the middle, and this has the effect that before you paste it here, you first flip it over the diagonal and then you map it over. So now you're getting G, this mapping G, it's going to map the same square to that open set, but it will face in the opposite direction. Okay, so that's going to be one way to do it. Another way you can do it is you can also negate one of the variables. So G of x, y, you can take maybe the first variable and negate it and keep the second one the same. So that would be another way you can do it. So the question of orientation is really a question of asking if the chart is facing the inside or the outside. Now, the problem is that in an abstract space, so in an abstract space, so a sphere, you can visualize an inside and an outside. But in an abstract space, there is no inside or outside. So we need some other way of, well, I'll leave it over here. The intuition of what it means for a manifold to be orientable is that we can find an atlas so that all the charts face the same side. We want them to face the same side. So we want them to all either face the inside or the outside. Now, in an abstract space, we have to sort of forget about this. That does not really make sense. Rather, we want to define what it means for them to all face the same side in a different way. So here is how we're going to do it. So we go back to the charts. So this is one chart, and here we have another chart. This is R2. So this is another chart, and let's say they overlap. So we're mapping a piece over here with another open set over here, right? We have this mapping like this. So the question we want to ask is, if this square is facing on the outside and this square is facing on the inside, then the transition function the change of basis, well, the change of variable function in moving from one chart to the other chart, it will have the following effect. This one is mapped sort of the correct way, correct in quotation marks. There is no correct here, right? So let's say maybe a little bit better to say is this one is mapped facing on the outside, whereas this one is being mapped so that the face is on the inside. And then that would mean that the way you move from this square to that square, there will be some kind of flip that occurs. There's a flip that occurs as you move from these, because when you move from that one, you face, let's say, outward, and then to move to the other one, you have to flip it over and then move back to that chart. So the map from this square to that square, it will flip things over. And that's what we're going to discuss. So basically, we need to figure out how to define a Euclidean map. Because whenever you deal with manifolds, you always bring back everything to the charts. You bring things back to Euclidean space. What it means for a Euclidean map from Rn to Rn to be, you can say, orientation preserving. Whether it keeps the orientation the same or does it undergo some kind of flip. So that's what we want to get. Okay, so the intuition here is when something is orientable, there is a way to map all of the charts into your space so they face the same way. We're not going to talk about inside or outside. That does not really make sense in an abstract space, but it would be possible to talk about it facing the same way. That's what we want to get to. And that's what we call an orientable manifold. And we'll make the definition, of course, more rigorous. So, and we want to define what it means to be orientation preserving. Now, just to give you an example of something that is orientable and not orientable is, of course, the sphere is orientable. Let me remove this. So examples of orientable manifolds. So I'll give you examples first. And these are going to be intuitive examples. We're going to start with intuitive examples first, and then we'll move on to proofs afterwards. But it's always a good idea to just start with the intuition first before we make things rigorous. So the sphere, as we mentioned, is going to be a orientable manifold for the simple reason because you can talk about, like, what you can do is at every point in the sphere, you can draw a normal vector. So this is just perpendicular to the sphere. So at every point, you can draw a perpendicular that points out. And what that means is, so the normal is, it consistently points in the same direction. And so what that basically means is that anytime you map a chart to the sphere, so let's say this is a chart, and I want to map this to a sphere. So you just map the chart to the sphere, and you get like a portion of the sphere. And then when you do that, that chart, when you map it to the sphere, it will either point, the face that you see, it will either point inwards or it will point outwards. If it points outwards, then that's good, right? So if this is your F, then that's good. You use that chart. However, if the chart points the wrong way, and the wrong way here simply means it points in the opposite direction of this normal, then you would just replace it by a new chart, G, where G is given by the formula that it's the original F, but let's say you just swap X and Y together, and now it points the right way. So the idea here is you cover the sphere with lots of different charts, right? It's a smooth manifold, so you cover it with lots of charts. And then for every chart, you just check whether the face that you see is pointing to the outside. If it is, you keep the chart, and if it does not, then you just change the orientation on that chart. And you do that for all of the charts, and then you have come up with a collection of charts, all of which point the same way. And that means that the sphere is orientable. That's like the basic idea of what that means. Another example would be the cylinder. And here you want to be a little bit careful. This is the open cylinder. This is the open cylinder because otherwise it's not a manifold. So it's something we've never talked about before. But like if you had let's say a cylinder that included its boundary, then the issue would be is at that point, if you look at the neighborhood of that point, then that would be homeomorphic. That would basically look like this, right? And then you can just enlarge it to like half space. So that would be, this is sort of like the other side of it. So this is sort of this is like R2, but you only have one side of R2 and not the other side. So it's not all of R2. And technically, this is called a manifold with boundary. But I do not want to define what that is. We're trying to keep this class a little bit easier, but it will just require more definitions. What exactly do we mean by a manifold with boundary? I think for now, it's just more convenient to just learn what a manifold is first before you move on to anything else. But just understand that the moment you start to include that boundary, it's close to being a manifold, but not quite. It's sort of the same issue when you have the closed interval and you have the open interval. The open interval is a one-dimensional manifold because all of these can just be homeomorphic to R because you always stay away from the endpoint. But the moment you include the endpoint, that is no longer homeomorphic to the real line. Okay, that's a different space. But it's close, like it's close to being a manifold. Call that a manifold with boundary. So technically, to be careful with our definitions, we're going to use a cylinder. And with the cylinder, you can do the exact same thing. At every point on the cylinder, you can draw an outward normal, like so. You just draw an outward normal. And by doing so, you can then you can just cover it with lots of charts. And you do the same thing. You just make sure that the side that you see is always pointing in the direction of the normal. And then when they overlap pointing in the same way, because they're both pointing in the direction of the same normal. So the cylinder is orientable. And now if you want examples of something that is not orientable, and this is the go-to example, and I'm sure you've seen it before, but we will actually prove this rigorously. So examples of a non-orientable manifold will be, of course, you have the classic example called the Mobius band. And this is perhaps the first example in probably math history of something that is not orientable. And it's the Mobius band, which goes basically something like this. You have that twist going through the band. And of course, we have to talk about the open Mobius band, because for the same reason, like the cylinder, its boundary has to be excluded. Its boundary has to be excluded, just like you have with the cylinder. Because otherwise it's technically not a manifold, it would be called a manifold with boundary. But anyway, this is the famous Mobius band. And the idea here why it's not orientable is that the common argument that people give, it's not a rigorous argument, but the common argument that people give is that, let's say you start on the outside, right? The normal is pointing out, and you travel all the way around the Mobius band, and by the time you come back to the point, right, you sort of, maybe to make it a little bit easier to see this, so you go back to the cylinder, and on the cylinder, if you start at a point and you go around, let's say, the center of the cylinder like this in a circle, you end up on the same side. But with the Mobius band, if you start here, you're on the outside of it, right, the side that you see. If you go all the way around it, then you will come back on the other side, even though you're at the same point. And we say that means it's not orientable. And then you have, of course, the projective plane. Projective plane. This is not orientable. We'll be able to prove that rigorously, why this is not orientable. You also have the thing called the Klein bottle. And the intuition here is actually very similar, because the picture that we have of the projective plane, it's kind of the same idea, that as you travel in like one complete loop, you end up on the other side of it. And the same thing with the Klein bottle, that you kind of can travel through that opening in the bottle and you end up on the other side. And that basically has to do with the fact that therefore the charts, when they overlap, they cannot face the same way. There is no way to orient it, because as you move from one chart to the other chart, it's as if you end up on the other side of the chart. So that's like the intuition for why these kind of spaces are not orientable. Now, another one that might surprise you, maybe surprisingly, P3 is orientable. So that might surprise you. So this three-dimensional projective space is orientable. And actually, the interesting thing about our definitions is all of our examples have been surfaces, but the definition will work for an arbitrary n-dimensional manifold. And that's going to be the nice thing about our definition. So even though you might completely lose all sense of intuition for much higher dimensional spaces, like we have no idea how this even looks like, you will still be able to carefully go through the definitions and show that this is orientable. In case you're wondering, P4 is not orientable, and it has something to do with even power and odd power. But this one, so this one would be orientable, and you'll see how to do it. We'll show the definitions, and then you'll be able to check it yourself. But what we want to get to is, we actually want to get to a rigorous definition to how to do that. So now that we've got the intuition out of the way, we'll discuss how to actually define it rigorously. We're going to need to discuss a little bit of linear algebra. Let's call this a linear algebra reminder. So why is that? So the reason for this is because if X is your space, and you're mapping Rn into X, and you have another chart that maps this into X, then we talk about the change of coordinate function from Rn to Rn. And we therefore want to ask whether the mapping between an open subset of this one and an open subset of that one is orientation preserving or not. And the way linear algebra comes into the equation is because the derivative is the, you can say, is the linear approximation to the function. This is true in single variable calculus, and it's also true in multivariable calculus. Like in single variable calculus, if you just have a function from R to R, and the function is differentiable, so let's assume that f of 0 goes to 0, so the origin stays fixed, and then your function is doing something. The derivative will give you that slope. Well, we'll give you that slope at the point, but then if you call that function, let's say L for linear function, then you're saying that the function f is approximated by the linear function. And this is sort of like the best linear approximation to the function. And it's very common in analysis to investigate the properties of your function by investigating the behavior of its linear approximation. That's how you prove a lot of the theorems about functions in analysis. And if it does not map 0 to 0, then you just sort of translate it. So if it's like, let's say it maps, then it's just going to be an affine version of it. It's not a big deal. And if you're mapping, let's say, R2 to R2, then, and let's say again, assume that the origin, so 0 here represents the origin, goes to 0 for simplicity, because a linear function maps the origin to the origin. If it does not map the origin to the origin, then technically it's an affine function, but an affine function is just a shifted version of a linear function, so it's not a big deal. So if this is satisfied, then the derivative of the function f prime at the origin, and the way you find this has to be a matrix, okay? This has to be a 2 by 2 matrix, because you want to get a linear function, and the linear function would be described by a matrix. So here the matrix would be, I assume you've seen this before, this is what you call the Jacobian. The Jacobian matrix, where you take the partials of your function. So your function f has two components, f1 and f2, right, because it's mapping into R2, and then you will take the first component, and then you take the derivative of it with respect to the first variable, and then you take the first component, you take the derivative with respect to the second variable, and then you do it the other way around. So that's called the Jacobian, and of course it gets evaluated at the origin, and that will give you a matrix. That's now a matrix. And if you, L is then the linear function given by that matrix, and then f is well approximated by that linear mapping. This is a two-dimensional linear mapping. But other than that, it's the same idea that you investigate the behavior of a differentiable function, which in this case we have a smooth function, by reducing it back to a linear map and understanding the properties of the linear map. So that's why we have to talk a little bit about linear algebra first, before we can say what it means for an arbitrary smooth mapping to be orientation preserving. So let's make this definition. Let A be a matrix, an n by n matrix. So we're going to think of A as the linear map from Rn to Rn. We're abusing notation. We're using the same symbol, one for the matrix, one for the linear map, because the matrix induces a linear map. You could maybe call this A star, the induced map from the matrix, but I'll just be sloppy. I'll call it A again. As a linear map. So this is the linear map that takes a vector in Rn, and it assigns to it Ax. So Ax is just matrix multiplication. You've all seen this before. When you do matrix multiplication of a matrix against a vector, you write the vector as a column matrix, and then you just do matrix multiplication. You get a column matrix, and then you write it back as a vector. That's all what that means. So you get a linear map out of that. So we say that A is orientation preserving if and only if. So you abuse notation. Sometimes you say the matrix is orientation preserving. Sometimes you say the linear map is orientation preserving, whichever one you want to refer to. So we say that the linear map is orientation preserving if and only if the determinant of that matrix is positive. If the determinant is negative, then you would say it reverses orientation. If the determinant is 0, then you just say it's a degenerate linear mapping. It maps the space to a smaller dimensional subspace. So then it would just be degenerate. It lowers dimension. So just to show you a very easy example of this. So here's an example. I'm going to do my examples in R2 because it's easier to draw pictures. Of course, our intuition breaks down the moment we get to R4, but the math is just fine. I mean, the math continues to work. R1 is too simplistic, not that interesting, so R2 is just interesting enough. We're going to fix an angle theta, and you're going to let A be a rotation matrix. So this is the 2 by 2 rotation matrix that has the effect of taking vectors and rotating them counterclockwise by an angle. And I think that's the way it goes. It's possible I messed it up, maybe the negative is there, but what the actual matrix here is does not matter. If it's wrong, you can just fix it. The idea is going to be the same. This is like one of those things I always forget. And then I have to rederive it. And after you rederive it like 500 times, it's no longer fun to rederive it. So maybe there's some kind of mnemonic here. You can probably write it in complex notation and Euler's formula and all of that, but that takes like a minute, and we're too lazy to spend that minute to actually figure out if it's correct. So this is a rotation matrix, and it gets its name because if you think of A as a map from R2 to R2, here's what it does. If you have one vector, let's call this vector V, and you have another vector, let's call that vector W, and there's an angle between them, theta, then, oh, I'm sorry, that is incorrect. Theta is something else. That's not the angle between them. There's some angle between them. We do not care what the angle is. You apply A to V. It will rotate it by a certain amount. That would be A of V. And then this one gets rotated by the same amount. Maybe I should not draw it like that. Maybe like this or something. This is A of W. Then the angle between them will be exactly the same. But what you should pay attention to is the orientation. Notice when you go counterclockwise, V goes first, W goes second. Same thing over here. V goes first, W goes second. You can also use your right-hand rule. So if you put the edge of your right hand on V and you curl your fingers towards W, then your thumb points towards you, towards yourself. And the same thing over here. If you put your right hand, the edge of your right hand over here, and you curl your fingers to the blue vector, the thumb points towards you. So the orientation is the same. And if you look at the determinant of this rotation matrix, you get cosine squared theta minus minus, so plus sine squared theta. And look at that, the only trigonometric identity we remember at this point, but we do know it is equal to 1. And 1 is bigger than 0, okay? So that means this is orientation preserving. So this is orientation preserving. Now let's give an example of something that is not orientation preserving. Let's say B is the matrix 0, 1, 1, 0. You can see that the determinant of B in this case is -1. So it will be orientation reversing. But to show you a very easy example, let's say this is the I vector that goes along the horizontal axis, and this is the J vector that goes along the vertical axis. Then by applying this linear map B, the effect would be that this one, so the coordinates of this are 1, 0, and when you do the matrix, right, this is going to be like 1, 0, right? That's vector. If you do the matrix multiplication, well, it gets 0, 1. You get the other one. So you would end up with that this is the image of I, and that is the image of J. And look at that. When you go counterclockwise, I goes first, J goes second, but now J goes first and I goes second. If you're using your right-hand rule, then if you put your right hand, the edge of your right hand along the red vector, you can curl your fingers towards J, and as you do that, the thumb points towards you. But now, if you put the edge of your right hand aligned with the red vector, the fingers cannot reach J. So you will have to align your right hand in a way so that the thumb points away from you, and then you can make your fingers curl to the other vector. So therefore, the orientation gets reversed. So that's just a little bit of linear algebra. And now we can define what it means for a smooth map. And by the way, it does not even need to be a smooth map. You can just talk about, let's say, a differentiable map. But we're talking about smooth maps anyway, so let's stick with smooth maps. So here's definition. We say that a smooth map F from, let's say, U to V. Here, U and V are open subsets of Rn. If you want to maybe simplify notation, you would just write Rn with a dashed line to Rn. So it's mapping an open subset of Rn to an open subset of Rn. So you would say that a smooth map is, and it's important to realize that the dimensions need to be the same here. We do not define orientation preserving with different dimensions, just like we do not do it with linear maps. Is orientation preserving? So this is the natural generalization of the previous one, if and only if the derivative at every point is positive. Now, what do we mean by positive? What we really mean is the determinant, because you get the Jacobian matrix, is positive for all points. Of course, if F is a linear map, then the derivative at each point would just be the linear map itself at that point. You might be thinking, is it enough to just check it at a single point? That would be enough if you knew that U was path connected, because this is a continuous function, and a continuous function will not be able to abruptly jump from a positive number to a negative number. So if you knew, for example, that this was, let's say, a diffeomorphism and this was connected, it's enough to just check it at a single point. But the thing is, this might not be a path connected set, so you want to be maybe a little bit more careful. You can maybe check it in the different path components. You can do it like that, perhaps. But we'll write the definition for every point. There are tricks you can do, so you do not need to check every point. But in some cases, often you will have a formula for the map, and you'll be able to calculate what this is. You'll be able to calculate the determinant. And after you calculate it, like in general, with a formula, you'll often be able to see that it works anyway. So the Jacobian, the determinant of the Jacobian is positive for all points in U. More generally, if you're using this simplified notation, you'll just say P in the domain of F. So this is called the Jacobian of F at P. I should just say a small disclaimer. There are some people who would define the Jacobian to just be this matrix. And there's other people who would define the Jacobian to be the determinant of that matrix. It just varies from people to people. We usually understand from context what we're talking about. So if I were to say the Jacobian is positive, then obviously I'm talking about its determinant and not the matrix. It would not make sense to say a matrix is positive, as that is not a number. Though there are some people who do say a matrix is positive if it happens to be positive definite. There's some people who do that, but let's not even go there. That's just not relevant for us whatsoever. You can understand from context what people are referring to. So if I was to say the Jacobian is invertible, then I'm probably talking about the matrix. Or if I was to say, let's treat the Jacobian as a linear map, then I'm talking about the matrix. But if I say the Jacobian is positive, then the reasonable way to interpret it is it's the determinant of that matrix. And then what is the derivative here? So what is f prime of p here? So it would mean that you're going to write f into components. So these are called component functions. And then the derivative at p, that would be a matrix. So it's a matrix. So the convention is often that I represents the row, j represents the column, that you will take the ith component function and you would take the jth partial and you will evaluate that at p. By the way, you could mess this up. If you happen to interchange them, it's not going to matter because that's the transpose. And the determinant of the transpose is the same thing, so it's not a big deal. So that would be the derivative at p. It's a matrix, and you just check if its determinant is positive. And that's the way we define what it means for a smooth map between two open sets to be orientation preserving. And now we can finally define what it means for a manifold to be orientable. Okay, so maybe I should just give a little warning. So when we say, so just a warning, that say X is a topological space and A is an atlas. But X with that atlas is not a smooth manifold. So in other words, the atlas that you're using for the charts, it does not satisfy the smoothness condition. So what's the smoothness condition? It just means that if you pick a chart and then you pick the inverse of another chart and you have this mapping, this is not smooth for some choice, for some indices, u and lambda in your indexing set. So if this happens, then you do not have a smooth, then this pair is not a smooth manifold. Okay, so let's say you have a space and you have an atlas, but the pair does not form a smooth manifold. It does not mean that X is not a smooth manifold. Okay, we could only say that X together with the atlas is not a smooth manifold. But when we say a topological space is a smooth manifold, what we mean to say is there exists a smooth atlas. So because it is still possible that there is another atlas A prime, so that X comma A prime is smooth. So maybe we can find a different atlas that will be smooth. So whenever we say that something is a smooth manifold, all it means is there exists an atlas that makes it smooth. Okay? So that's when we just talk about X by itself. Orientability is going to be the same way. When we say that a manifold is orientable, it will mean there exists an atlas, a smooth atlas with a certain property. Not that if you have a particular atlas, it's going to be orientable right away. Okay, so let's make the definition. Let X be a smooth manifold. Well, we say X is orientable. If you want to add more detail, you can say an orientable smooth manifold. And you can even say an n-dimensional manifold, but then you're just adding too many words. Let's just have the convention that anytime you see orientable, it's referring to a smooth manifold. It is possible to define orientable in a topological way that is a lot more general, but that's typically not what we do anyway. In topology, anytime anyone throws around the word orientable, they almost always mean manifold with a certain property, unless they're doing something like hyper specialized. But this typically is what it means. So we say X is orientable if and only if there exists a smooth atlas. I'm going to start getting sloppy. I will begin to drop the word smooth. So I will just say atlas, I will just say manifold. It will understood that things are smooth. If things are not smooth, then we will overemphasize that things are not smooth. But in general, in the subject, we just assume that things are smooth. If and only if there exists a smooth atlas, maybe we can call this atlas script O, because O for orientable. There exists a smooth atlas O consisting of functions, let's say, of a family of functions. So it is an atlas with an additional property, a smooth atlas with an additional property. With the property so that O is an atlas, right? We want it to be an atlas. And if you take the change of coordinate functions, then there'll be a map from an open subset of Rn to another open subset of Rn. So this is a diffeomorphism. Well, yeah, it's a diffeomorphism between two open subsets of Rn, right? This is a smooth map between two open subsets of Rn. This is the change of coordinate function, change of coordinate mapping, that this is orientation preserving. So in particular, its Jacobian will be positive at every point in the domain. And this is for all choices in the indexing set, lambda. So no matter what two charts you pick, this condition is satisfied. Of course, if this is empty, if this is the empty function, right, that this could be the empty function, when the, like for instance, phi lambda and phi mu, the images of the charts do not overlap, then this composite function is the empty function, but then it's mapping an open subset of, it just maps the empty set to the empty set. It's just the empty function mapping the empty set to the empty set. And that will be, it's orientation preserving just for trivial reasons, because there is no point to pick in the domain to check that the Jacobian is positive. So this condition is going to be satisfied. Okay, so this is the definition. It's a nice, satisfying definition. It agrees with our intuition. This is working up to everything that we've been saying up to this point. Okay, so we say a manifold is orientable if there exists an atlas with this property. It does not mean that just because you have an atlas and that atlas is not an maybe we can call such an atlas, let me add over here. So we say O is an oriented atlas. So how about that? Let's just add that to our definition, an oriented atlas. So when you have an orientable manifold, it has an oriented atlas. It is quite conceivable that you have an orientable manifold, but the atlas that you're using is not oriented. That does not automatically mean that the manifold is not orientable. Orientable just means there exists an oriented atlas. Maybe you can replace that atlas by something else that will be an oriented atlas. Okay, so that is the definition of an oriented atlas. And I want to give another disclaimer, something to be careful about. So here's another disclaimer. There is no such thing as positively oriented. That makes absolutely no sense in an abstract space. So you will never say something like, let O be an oriented atlas with, let's say, positive orientation. That makes no sense whatsoever. In an abstract space, there's no such thing as an inside and outside. We cannot see anything anymore. The only thing we can talk about is we can talk about whether or not the charts in the atlas are consistent with one another, in the sense that the transition maps between the change of basis is orientation preserving or not, whether or not there's any flipping that occurs in the change of basis, in the change of coordinates in the charts. We can talk about that, but we never ever talk about something being positively oriented. Now you might find this confusing because a circle, right, a one-dimensional circle, that's a one-dimensional manifold. And we're about to do an example after this, but someone might say that, as you go around the circle like that, that gives it an orientation. And some people will say this is the positive orientation because you're going counterclockwise. But here you have to understand that a circle, it's a very concrete space that you can see. And also because a circle, you can embed it in the plane. And when it's in the plane, you can think of it as a loop. And when you have a loop, then you can talk about a loop going around in the positive way or in the negative way by looking at the winding number, things like that. A circle is just a very simplistic type of space. It's the same thing when you have like the sphere. If you ever taken like vector calc, like in physics or vector calculus, maybe you had like a professor or something that said that the outward normal vector is positively oriented. So in physics or vector calculus, whenever you do those calculations with like the line integral or a surface integral, which we're going to get to, by the way, we're just going to define it in a much more general way using differential forms, but we're going to get to that, that you would have to pick. So if you have like a certain chart for that portion of your surface, you would pick your, you would have to choose a type of chart that points to the outside, and that's the way you orient it. But this is an arbitrary choice, and you can only talk about something being outward because you have a sphere, you have something you can visualize. In an abstract space, such a thing does not exist, okay? So we only talk about things being either being orientable or not, right? That's what we talk about in the abstract in general. So now that we've made these definitions, it's nice to move on to some examples, which we do rigorously by using these definitions very carefully. We're going to do a very simple example where we're going to show S1 is orientable. And it's not surprising, of course. Like It's not like we're shocked by this statement or anything like that. But rather, the purpose of this example is to carefully use the definition, because that's how we improve our mathematical skills, not just to look at it and say, well, that feels correct and move on, but to show how the definition is being used very carefully. And we're going to use the atlas that we've used already a number of times for the circle. And that was the atlas that consisted of what we call the positive chart. And the negative chart. The positive chart was the mapping e to the 2 pi I s. And it was defined on the open interval. And the negative chart, we use the variable t to denote it so that we can distinguish between which chart is what. We can, of course, keep on using the same letter, of course. It's just convenient to switch it up so it's easier to distinguish between them. And this was negative e negative 2 pi I t. And yes, so this was f minus into S1. And the picture that we had was the positive chart. It takes the open interval from 0 to 1, and as we move from 0 to 1, that's the orientation, and it will wrap it around the circle in a counterclockwise way. And the other chart, it will take the same interval and will also wrap it around the circle, but just beginning at a different point and also in a counterclockwise way as well, like this. So you can see that these, so this is just the missing point. This is the missing point. So individually, both of these charts do not cover the whole circle. That's why you need both of them. These are homeomorphisms onto an open subset of the circle. But if you look at how they overlap, notice they keep on following the same direction when they overlap. So because of that, we would say that it should be, this is an oriented atlas. But to carefully show the definition, what we need to do is we need to check the change of coordinates. So here there's only two charts to use. So we have f plus composed with f minus inverse. You really have to do it for 4 combinations. You have to do f plus composed with f plus inverse, but then there's nothing to check. That's just the identity. The same thing with composing f inverse, f negative with its own inverse. But the interesting thing happens is that if this is orientation preserving, then there's no need to do it the other way around. There's no need to then check that this is orientation preserving, because that's basically like the role of the inverse matrix, right? If a matrix is orientation preserving, its inverse is also orientation preserving because its determinant is just 1 over the previous one, which is still a positive number. So it's enough to just check that this is orientation preserving. And we saw that this composition, it's not actually defined on the entirety of the circle. It's defined in an open subset of the circle, and it's defined on the union of these two open intervals like this. Maybe I should make this a little bit more explicit. And this is the mapping that we saw before, that if this is called, if we call this S, right, this is like the S coordinate because we're starting in the S chart, and we map it to the circle and then we bring it back, so we're finding the T coordinate, right? We bring it back to this, to the negative chart, so we're finding the T coordinate, and the T coordinate, it just, so it will become either S plus a half or S minus 1/2, depending on whether S is in this one, then it gets shifted over to that one, and if it's in that one, then it gets shifted back to the other one. So that's the way this mapping is defined. And now you have to calculate the Jacobian. So here the Jacobian is just the ordinary single variable calculus derivative. So the derivative, so you would write f. So if you just write out what this function is, this is the function which is s plus 1/2, s minus 1/2 with some conditions. And then this function is smooth. And if you calculate its derivative at any point, let's call that point s again, then the derivative will always be equal to 1. Because the derivative of both of these works out to be 1 regardless of which case you're in, which is a positive number for all s. Okay? And by the way, it just illustrates that the situation that we were saying, that this change of basis mapping, it might be defined on an open subset which is not path connected. But in this case, it does not matter, that regardless of what you pick for s, it's always going to, the Jacobian will always be positive. So therefore, this atlas is oriented. Notice, I'm not saying it is positively oriented. We only talk about it being oriented. So thus, S1 is an oriented, actually is an orientable, You're not going to say it's oriented. Oriented is on the atlas. Orientable is a property. S1 is an orientable one-dimensional manifold. Actually, an interesting question you can ask, are all one-dimensional manifolds orientable? And the answer is yes, because we have something called the classification theorem. There is a classification theorem for these, and the classification theorem says that every path connected, you can even say connected, but every path connected one-dimensional manifold is homeomorphic, and you can even say diffeomorphic to either R1 or S1. If it's compact, if your manifold is compact, it's going to be homeomorphic to S1. If it's not compact, it's homeomorphic to R1. And if you're wondering about what happens if you have something like that, that is not a manifold. That is technically called a manifold with a boundary. So we do not include that in there. But you can also generalize the classification theorem a little bit to include that. This is actually surprisingly difficult to prove. Like, you would think that it feels like it should be something simple, but it's not, because you are, after all, talking about abstract spaces, so they do not necessarily sit anywhere. And when you understand that you're talking about spaces in the abstract, then you suddenly start to understand that it should be difficult. The way you prove this is, there's like two versions of the classification. There's a topological classification theorem where you do it for homeomorphic, with the assumption it's homeomorphic to R1 or S1, but without using anything about smooth manifolds. But then you need a triangulation theorem that says that every one-dimensional manifold could be triangulated. There is a way to do it without triangulation. There's a very famous book by Topology by John Milner. It's called Topology from a Differentiable Viewpoint. And it's proven in the appendix. He proves this in the appendix. And his proof, he does not even use triangulation. He does it with using diffeomorphisms and things like that. The fact that you have a smooth manifold and the fact that you can use calculus, he takes advantage of that, rather than making it only using by using only topology, kind of takes advantage of the calculus. The book is very short. It's about 60 pages. And that's actually why it is one of the most famous books ever written on math because it's so short. The longer your book is, the less people are interested in it. So if you want to make a book that's more popular than John Milner's book, make your book be 30 pages. If you're wondering if there's a math book that's 30 pages, yes. There's like a 30-page book called the Gamma Function, written by a very famous mathematician, Emil Artin. I think that's the shortest math book that I happen to know. There's some other very short math books. I think the smallest, if you're talking about graduate text in mathematics, I think there's a book that's around 70 pages. It's also very popular because it's a small book. I think it's called like analytic number theory. Maybe there's some other subtitle to it. And this is by Donald Newman. If you want another book, it's about maybe 110 pages. It's called Course in Arithmetic. So this, I did read Topology from a Differentiable Viewpoint. I never read the Gamma Function book, and I never read this one, but this one I read, Course in Arithmetic by Sayre. This is also one of the most famous books in the GTM series. So anyway, that's just some interesting facts about books. It's nothing to do with what we're doing, but just some interesting information. Yeah, so it's by John Milner, Topology from a Differentiable Viewpoint. In the appendix, he proves to you this classification term. And because these are orientable, it means that all one-dimensional manifolds are orientable. But the moment you reach two-dimensional manifolds, you can see things get immediately more complicated, and it's not necessarily true anymore. Now, I want to continue with this example by showing you something else. So let us use a different atlas for the circle. So the previous one was using Euler's formula for the atlas. Let's do the one that was on the homework, and this is the one where you have to do it with stereographic projection. So here we're going to have an atlas consisting of two charts. One of them we call Fn for the North Pole and Fs for the South Pole. And without writing out the formulas for these, because you have to do this on the homework, so I assume you figured it out. The North Pole mapping, so this is S1. Okay, this is S1. You draw this line here. You're going to call this R. And this is N for North Pole. And let's say Fn. Let's give the variable a name. So let's call this, just like before, let's call this the S variable. And this is going to be a map from R. So in the previous example, it was the open interval from 0 to 1. But when you're using stereographic projection, you actually are using all of R. This is going to be mapped into S1. And instead of writing down the formula, we'll just draw a picture. So if this is S, right, this is your S on the real line, you draw that, and where it intersects, you're going to call that Fn of S. So once you figure that out, that would be the formula for that one. And the other one, let's call it T, Fs. Well, I can kind of see calling it S, conflict of notation. Should we keep it S or should we call it something else? Let's, yeah, maybe we should call this, let's call that U. Okay, we'll call that U. So it's going to be U, and that's U. And for the other one, this is going to be V. Well, we also have an S over here, but let's not get too worried about that. So for the other one, you have the South Pole. And the way this one works is if you have, let's say, V, does not matter where it is, you draw the line. And where that intersects, you call that Fs of V, like that. And let's intuitively, so let's do this. So let us check without using the Jacobian, which in this case is just the derivative, since this is a one-dimensional problem. Without using the Jacobian, let us first use our intuition to check if this atlas is oriented. And obviously the answer is no, because we just did an example with something that was an oriented atlas. So obviously, for learning purposes, I have to give you something that is not. I mean, of course that's what's going to happen, but that would be cheating, right? Because you saw what happened before. Let's say I did not give the previous example. So the way you can think of this is just, it's what we did in the previous example. Let's just see what happens with the real line. So the real line, so imagine the real line goes from negative numbers to positive numbers. And then how does this real line get mapped using Fn? Well, you can see that as you move from left to right, so as you move from left to right, maybe I should remove all of this so it does not get in the way. Like this. So if you have a point, like up here, it gets mapped there. And if you have a point over here, it gets mapped there. So you can see as you move from left to right, you're moving counterclockwise. So you're going to miss the North Pole. That's the point that is not covered. And you're going to move like this, counterclockwise. And the other chart, Fs, let's see what this one does. So for the other chart is, let's say we have a point over there, and it ends up here. And if we have a point over here, maybe I should do that again. So if we're on the left, we're there, and if we're here, then we're there. So you see what's going on, that as you move from left to right, and you look at the points the way they get mapped to the circle, then you're moving clockwise. So then the image of the real line, so let's orient the real line from negative to positive, you get the circle, you get the missing, so you get the circle, the uncovered point here is the South Pole, and this time this one moves clockwise. So you can see from here that so the transition function from this coordinate to that coordinate, it will require you to sort of flip things over, and so the mapping from R to R is not orientation preserving. Now, if you did the homework problem, then you should have found, so you have to check Fn composed Fs inverse, and you have to determine, so basically the question is this: if I give you a point on the circle, which is part of both charts, and I know the value of u, right? I know the u coordinate. Well, that very same point, it also has a v coordinate. And the question is, what is the relationship between u and v? What is the change of coordinates that occurs? That's what this composition is supposed to represent. Now, the actual composition, it's not defined on all of R. It's actually defined on the punctured reals to the punctured reals. It does have to miss the origin. And this should make sense, of course, because the origin with the North Pole, if you're projecting to the North Pole, it will hit the South Pole, but then the South Pole is missing. So the origin has to be the one missing point that has to be omitted because it's not covered in both. And as a function, you have to determine v in terms of u, and if you did the exercise, and you can probably maybe even guess what this is because you have a reciprocal. So this is actually 1 over u. So you basically say So that like often what you would write is you say the v coordinate is 1 over u. This is supposed to represent that if you have a point on the circle and you know the value of u, you know the u coordinate, you can recover the v coordinate by just taking the reciprocal. So we have this function, and now we have to take the derivative of this function. So we're finding the Jacobian. In this case, it's a lot easier. It's just a single variable function. So the derivative of this function, so it's the derivative of the reciprocal function, negative 1 over u squared. And what we see over here is that this is negative for all u. It's negative for all u, because this is being squared, so this will be a positive number. So this is negative for all u. So thus, this atlas Fs, Fn is not oriented. And now to get back to the point that I wanted to say again, however, the circle is still orientable since it has an oriented atlas. So it just means that this atlas is not oriented, but you can make it be oriented in a very simple way. Like one thing that you can do here is you can replace this function by a slightly different function that you just replace v by negative v. So you would just replace this, you would just basically replace this function by a new function, let's call it g, so that g of v is fs of negative v. And then that will have the effect that the v coordinate would just be the negative, it would just be the negative of the previous coordinate, and now when you take the derivative, you get something positive, right? So you can always you can change it so it becomes oriented. So this is an example of something that is orientable, and we gave an example of an oriented atlas and a non-oriented atlas for the same space. So now let's move to the Mobius band and prove that the Mobius band is not orientable. Let's state the theorem that the Mobius band is not orientable. The Mobius band is not orientable. The Mobius band happens to be a smooth manifold, as we will show. That's not difficult, but the difficult part is to show that it's not actually orientable. And we're going to do this rigorously. So the interesting thing about this is that often many books, classes, they never prove this rigorously. And I just find that very interesting. When I was in graduate school, I've just heard that assertion so many times, but no one took the time to write out a fully rigorous proof. They just did that same kind of argument where they would say that if you have your Mobius band, so it's the argument that we've said before, that if you have your Mobius band, and if you have a vector, like a normal vector that's pointing on the outside, that's one side of it, as you move around and you return back, it's now pointing on the other side. And it's nice to give that intuition, but it's more important to show how the definitions are being used. And for some very unusual reason, no one ever done anything like that. And I'm going to show you a rigorous proof where we carefully go through the definitions and we show that the Mobius band is not orientable. Just a small disclaimer, usually when people talk about the Mobius band, they talk about this space including the boundary. Technically, that's a manifold with boundary. And the way we're using the definitions is we're just working with manifolds. So we're just going to modify the space by avoiding this boundary curve around it. And then we would have what you can call like the unbounded Mobius band. But once you learn what a manifold with boundary is, you will, of course, be able to go back to this proof and modify it and show that the classical Mobius band is not orientable. So this is what we're going to prove. We first have to define what the Mobius band is rigorously, and then we have to show carefully how the definition is being used. So that's what we're going to go through. Now, this proof that I'm going to show you This is a proof I found several years ago on Math Stack Exchange that was given by Christian Blattner. He was a German mathematician. He's not alive anymore, but he was an active member on that site, and he would answer people's questions. He was old, but he would answer people's questions. And I accidentally, many years ago, came across a proof of his for why the Mobius band is not orientable, and I was very impressed with that proof. There was a completely rigorous proof. There's no hand waving, there's no picture drawing, there's none of that. It's very satisfying. You get to see how the definitions are being used. And the proof is not long, but it's not something that's easy to come up with. So the first thing that we need to do is we actually have to define the Mobius band before we do anything. So there's different ways you can define it. We're going to do it in the following way. So let X be the space R times -1 to 1. I'm going to be using an open interval because we're going to be creating a Mobius band without boundary. So this is an infinite strip, or an infinite band. So of course, the way this would look like is your space X would just be these two lines that are shaded in. So that would be X. And then you're going to twist that into a Mobius band. And we'll do that by using an automorphism. I'm going to let alpha be a map from X into X. This is going to be an automorphism. And it's going to take a point, X comma Y, and it's going to send that point to X plus 1. So you're going to shift X and you will negate Y. So this would be your automorphism. And it's not difficult to check. And you're going to let G be the group of automorphisms that's generated by this alpha. And because you only have a single generator, and by the way, no matter how many times you ever iterate the generator, you will never return back to the identity because X just keeps on being shifted over. So this no power of alpha will give you the identity. So this will therefore be, as a group, that's of course isomorphic to the group of integers. So the way you define the Mobius band, and then we define the Mobius band, let's call it M. So we're going to define that as the quotient, X mod G. Now, this is the one way how you can rigorously define the Mobius band, but let's just give some intuition for what we're doing. So the idea here is when we go back to this infinite band, so this is our infinite band, where we're located between -1 and 1, you have to understand that you only have to consider the region that goes from 0 to 1. Because if you go beyond this, you return back. It's equivalent to what you had before. So like, let's say you have a point right over there in the band. Well, that point will be equivalent. You can shift it over by 1, but then you would negate it. So you would be down here. So that point is equivalent to that point. Likewise, if you have a point up here, that point would be equivalent. You will shift it over, and then you will negate. It will be equivalent to that point. So what you can see from here is every point in X will be equivalent to something within this square. Okay, so that means you can focus on just this square. So every equivalence class is represented by something, by a representative somewhere within that square. And now, if you pick a point, let's say on this boundary, then that point will be equivalent. So you shift it over by 1, and then you negate. So this point is equivalent to that point. However, the upper edge and the lower edge, they're not equivalent to each other because there is no upper edge or lower edge. This is the Mobius band without any boundary. And so the intuition here is you basically get a square. You have the upper and lower edges not being included. And the orientation that you're putting on the edge is that if this one, they're kind of going in opposite ways. So the point on top corresponds to the point down there. So when you glue them, you do not glue it like a cylinder. You have to twist in order to glue it. And so when you do that twist and you glue it, you end up getting the Mobius band. So this is one way. There's, of course, many other ways, but this is one way how you can rigorously define the Mobius band. So that becomes your topological space. And furthermore, we have a quotient map. And we have we have the map pi from X into the Mobius band. And what does this map do? Well, a map just sends it to its equivalence class, right? So if you have a point in the infinite strip, you just send it to its equivalence class. Okay, so this is the quotient map. With the quotient map, you can then topologize this. So you would say something is an open set of M if and only if it pulls back to an open set of X. So this is then a continuous map. This is a topological space and all of that. So we have a topological space, we have a continuous map, but we want to turn this into a smooth manifold. So furthermore, M is this is going to be a two-dimensional manifold. It's a two-dimensional smooth manifold. And we can find an atlas with only two charts, And I'm going to show you how to do it, but I'm going to also make a homework problem based on this, where you'll have to check something. So on the homework, you will check that it's actually a smooth atlas. It's not difficult, but this is the way you do it. You're trying to find an atlas for M. So you're trying to find a way to map R2 into M, right? And you're going to have two charts. One of them you can call like phi1, that's your first chart, and you'll have another chart you're going to do phi2. So it's going to be, so both of these are going to be homeomorphisms of R2 onto an open subset of M, and their images, the images of the charts will completely cover M, and furthermore, the change of coordinates that occurs from those two charts will be a smooth map. So this is the way that you do it. Here, it would be convenient not to use R2, but to use something a little bit smaller, just for the sake of notation. But the way you're going to do it is you're going to use the original X, right? You're going to use X. So we have this map from X into M, and we have that mapping pi, okay? So you have this infinite strip. We have this infinite strip, and you're just going to restrict that infinite strip to the following open square. So you're going to go from 0 to 1, okay? So the horizontal coordinate goes from 0 to 1, and the vertical coordinate goes from -1 to 1. So this is going to be, so you can call this, yeah. And then if you restrict pi to that region, you're going to get a homeomorphism. So if you do, let's say, 0, 1 times -1 to 1, and you map this into M using pi. So I'm calling this pi, but all I'm doing is I'm restricting pi to that open subset of X. So this is, of course, something that's homeomorphic to R2, right? This is just an open square. Then this is going to be a homeomorphism. This is a homeomorphism onto an open subset of M, of the Mobius band. The reason for this is because this is a one-to-one map. The left edge and the right edge are not being used. So there is no gluing occurring. So this is going to be a homeomorphism. So, but that does not completely cover the Mobius band because these left and right edges are being omitted. So what you do for the other one is you slightly shift it over. So then you're going to have another chart that's going to be just slightly shifted over like this. So that would be your other chart. It will be slightly shifted over. And then you'll have the other chart that will go from, let's say, or I mean, you can shift it to the right, but you can also shift it to the left. I think maybe it would be better to shift it over to the left. So it's just maybe the notation comes out a little bit better. So we can kind of draw it down the middle like this. And then you'll have another chart that goes from -1/2 to 1/2, -1 to 1, and you map it into M using the same map pi, but you're just restricting it to a different domain. And this will also be a homeomorphism onto an open subset of M. And now everything is covered, right? Because the last piece that was missing, that was that edge, it's now included in the red piece. So now everything is covered. So these two charts, they're mapping something that's homeomorphic to R2 into the Mobius band. And you can check that these two mappings, phi1 and phi2, which are just the restrictions of pi to these open sets, that will be a pair of homeomorphisms whose change of coordinates is a smooth map, right? So that's something for you to check on the homework. It's not difficult, but that's the way you would do it. So M happens to be a two-dimensional smooth manifold, okay, with two charts. So, however, this atlas, so this atlas of these two charts, of those two charts, is not oriented. It's not an oriented atlas. You will be able to check that on the homework. So again, you'll just find the change of coordinates and you will calculate the Jacobian. And when you do that, you will find that the Jacobian comes out to be negative at every point. So it's not going to be an oriented atlas. However, you want to be careful. That does not mean that the Mobius band is not orientable. But be careful, but we need to be careful. To be careful and rather show that there is no oriented atlas. Okay, we cannot just pick an atlas and say it is not oriented. We have to show there is no oriented atlas whatsoever. So observe that pi from x to m is also a smooth map. This is not difficult to check. I think this would be a good problem on the homework. We talked about what it means. So basically, so X is a smooth manifold for the simple reason because it's already an open subset of Euclidean space. This is a smooth manifold. M is a smooth manifold because we just explained why it's a smooth manifold without working through the details, but that's something you can check. So these are both smooth manifolds. And we previously gave a definition in class about what it means for a map between smooth manifolds to be smooth, right? You basically just check that it's smooth when you compute the map with respect to each chart. That's all you have to do. So, and I mean, it basically has to do with the fact that the charts for M were coming from pi itself, restricted to those open sets. Okay, so that's what we have. So this is a smooth map. And we claim, okay, so let us assume for sake of contradiction, so we're going to assume by sake of contradiction that there is an oriented atlas O for M. And we're going to use that to get a contradiction. So let's say that this atlas O is a collection of maps like this. And the assumption would be that the change of coordinates between any two of them will have positive Jacobian. So this is at the moment the setup. So now we're going to try to take that intuitive proof and convert it into a rigorous proof. So the intuitive proof is, as we've said, this is the way you show that the Mobius band is not orientable in an intuitive way, is you argue that if you travel around, so let's call that the belt of the Mobius band. So the belt is the line that runs straight through the center. So the belt. So if you're on the belt of the Mobius band, you pick a normal. So let's say you're pointing to the outside. And then as you point to the outside and as you kind of go back in, when you return back in, suddenly you're pointing on the other side. So that's like the intuitive argument that we use for why it's not orientable. And we want to make this argument rigorous. So here's what we're going to define. And this is going to hopefully give you a little bit of motivation for what we're about to do. So we're going to define a function. And I'm going to call this function sigma. Sigma for sign, positive, negative. So this is going to be a sign function. This is going to be a function that's going to map the real line into 1, -1. And before I give you the way this function is defined, I want to give you the motivation for what we're doing. This is the Mobius band. And the way we're getting the Mobius band is we are starting with x, and we're introducing this group of automorphisms, and that the quote is how we get the Mobius band. So the idea here is we have a map from x, right? So this is m, and this is x. Okay, so x is this infinite band. So I'm going to draw the infinite band with solid lines, only because it's just easier to see, right? Technically, of course, these are supposed to be broken lines, and the boundary is supposed to be a broken line, but it's just easier to draw this way. And we have our map pi. We have our projection map. If you want to get the belt, you just move down through the center like this, right? You're moving down the center. So as you go down the center of the strip, the image of this on the Mobius band will take you around the belt, right? So you kind of infinitely wind around the belt as you go around. And so you see the sigma function is being defined on R because this is basically R. Now, it's not exactly R. If you want to be a little bit more specific, it's R times 0, right? The vertical coordinate is going to be 0. But if you ignore the vertical coordinate, it's just R. So it's going to be a mapping from R to 1, 0. And the idea is that as you move across the belt, you're somewhere on the Mobius band. And so the normal is either pointing to the outside or to the inside, and you will assign 1 or -1 depending on which way it is pointing. And we're going to get a contradiction out of that somewhere. But for now, let's define such a function. So here's how the function is defined. So let me remove the blue pieces. They're just going to get in the way, like this. So here's how this will proceed. So we're going to define a function as follows. So I did not tell you how to do that yet. The picture here is just a motivation for how you come up with this function. So what you would do is you're going to, for x in R, right? So let's think about this. We're trying to define this function sigma, and to define a function, I pick a real number, let's call it x, and I have to tell you how to map that real number. So I'm going to pick a real number somewhere along that strip, right? I pick an x, right, lowercase x. So that makes me end up somewhere on the Mobius band. Now the actual location is going to be pi x comma 0, because we have to understand that on the actual band, the vertical coordinate is equal to 0. So for x and R, we have that pi x comma 0 is a point on our Mobius band. And since we have an atlas, okay, that means there's a chart that contains it. So there is a chart, let's call it phi lambda. Actually, I call those F, does not really matter. There's a chart F lambda from R2 into M, so that this point is on the image of that chart. Okay, so maybe I can redraw the picture again so we get a better idea of what we're trying to say. Is we have our Mobius band like this, and we have a point on the Mobius band right over here. I'm not going to give it a name, it's just that point right there, and it is in a chart. So there is some open set that will contain it. So that would mean that there is an R2. This is a two-dimensional manifold. So there's a copy of R2 that is being mapped. I call this F lambda. That is being mapped homeomorphically to that open set, and the point is sitting inside that open set. Okay, we have this. And we're going to bring everything back to the Euclidean world. So notice we have a mapping pi from the infinite strip. It maps it to the Mobius band. And then we have a mapping from R2 into there. So if we go pi first, so if we go pi first, and then we compose it with the inverse map, which exists because this is a homeomorphism, we will then get a map from pi, from the infinite strip to R2. So then, if you do, so if we go pi first, and then we compose it with f lambda inverse, then that would be a map. Now you have to understand that this region, the corresponding open set, when you pull it back using pi, that would be some kind of open region in X. And then this composition will map that open region in X to an open subset, right, to an open subset of R2. But to keep the notation simple, I'm just going to write that whatever this is, X is, of course, an open subset of R2. So whatever this region is, it's an open subset of R2. We do not really care what it is other than the fact that it's an open subset of R2. So I'm just going to write it like this. I'm going to say that this composition maps R2, and I'm going to use the broken line into R2. So all this means is this composition is mapping some non-empty open subset of R2 homeomorphically onto another open non-empty open subset of R2. In fact, not just homeomorphically, but this is a smooth map, right? This is a smooth, it's smooth. So the reason why this is a smooth map is for a very simple reason, because pi, right, pi is a smooth map between manifolds. This is a smooth map, right? And so the composition of smooth maps is going to be smooth. I mean, basically, it just comes down to the fact that the definition of something being smooth. So where was this? Yeah, right, like right over here. So the definition of something being smooth on a manifold level basically just means that when you compose with charts, you get smooth maps. Okay, that's what that means. So we're going to have some kind of smooth map over here. And this mapping, this will be an open set, and it has to contain, it's an open set that contains x comma 0, right, the point that gets mapped to it. So then here's the way we define sigma. So we define sigma of x. This is just going to be the sign of the Jacobian, right? So we're going to take this mapping. We're going to calculate its derivative at x comma 0, and it'll just be the determinant of all of that. So it's the sign of the Jacobian. It will either be positive or negative. If you're wondering why it's positive or negative, well, because this map is a homeomorphism, and in fact, it's a diffeomorphism. And when you have a diffeomorphism, then the Jacobian cannot be 0. It's sort of just like linear algebra, that if something is invertible, the matrix is invertible, the determinant is not going to be 0. This is like homeomorphism. In fact, it's a diffeomorphism. It's invertible, so that's the reason why it cannot be. So it's either a positive number or a negative number. So the whole idea here is basically this. This is the intuition. You're having a map from the strip down to this one, and it's a question of whether or not the mapping, right? You have some kind of mapping from here to here, and it's a question of whether or not that mapping flips the strip over or it keeps it in the same orientation. That's the whole idea, and that's basically the intuition for what we're trying to say, of whether or not the normal is pointing on the outside or whether the normal is pointing on the inside. We're just making it rigorous as we do it. Okay, so this is the way we define this sigma function. Okay, so let's maybe go through this step again. So we're defining this function called sigma. This is the sine function. It's defined on R. The idea here is you run around the belt, right? You move along the belt. So as you're moving along the belt, you map a point onto the Mobius band, and then you're going to decide whether or not that point is on the outside or the inside. Now, how do you decide if it's on the outside or the inside? You're going to use a chart. That point, there it is, it's part of a chart. Okay, so you pick a chart, a lambda chart, whose image contains that point. And then if you do this composition, then you're going from the band to R2, right? And you have this diffeomorphism, you have this smooth map, and then you just calculate the Jacobian at the point at which you have. And the sign of the Jacobian will tell you whether or not you're on the outside or inside of the Mobius band. So that's kind of like the intuition for what we're doing. Now we reach a very critical point of this argument, is that we claim that sigma from R into 1, -1 is well defined. So what do we mean? So we're going to say suppose pi x comma 0. So we pick a point at x, you map it to the Mobius band, but let's suppose that point is in a different chart. Let's say it's in the mu chart, right? In a different chart, because we are choosing a chart, right? We're saying there is a chart. There is a chart. So we're picking a chart. What if we picked a different chart? So we obviously have to use the fact that this is an oriented atlas somewhere in the proof, because we did not use that yet. So we're going to suppose the point is in a different chart. So then look at what's going to happen. What is the relate? So we have, so maybe to draw the picture again, let me draw the picture for you. Let's go like this. We have a point. Let's say we have a point over here. We have some chart. This is mapping R2 homeomorphically over there, F lambda. But now we say, let's say you have another chart that overlaps with it, and it also contains the point. So then you have R2 going in there. This is F mu, like that. And we have change of coordinates between the two charts. So that would be F mu inverse composed with F lambda, like that. And what we know about this map is that this map from that chart to that chart is orientation preserving, because that's the assumption of what it means to be an oriented atlas. So we have the following relationship. So on one side, we're going to have F lambda inverse composed with pi. But we can also say that this is F. We can also write it like this. We can write this as F mu inverse composed with F lambda composed with F lambda, F mu inverse composed with pi. So this is not correct. However, we can put it on the other side. So what I should do is I should put mu over here, and I should put lambda over here. And then you can see that everything works out, right? This is equal to, right, because when you write it like this, that cancels, and then you're left with that. Okay, so it works out. Now, why are we doing it? Well, the reason why we're doing it is, let's go back to the definition of how sigma is defined. You do this composition, you calculate the derivative at x0, and then you find the determinant of that. Okay? Well, you also have to do it using the mu chart, right? So this is what the mu chart. So it follows from here. So now you're going to use the multivariable chain rule, which is just like the ordinary chain rule. So thus, the derivative evaluated at x comma 0, that would be equal to, so it's a composition of two functions. So it's going to be the composition of the inside function, its derivative at x comma 0, and then you're going to multiply it by the composition of the derivative of the outside function, and it gets evaluated. So it gets evaluated somewhere, right? It gets evaluated somewhere, and the point that it gets evaluated is, we're just going to call it p, right? Where p, so what is this p? We do not care what it is, but the point is that p is just the inside function evaluated at x comma 0. So on the picture, you have x comma 0 somewhere. Yeah, it's just, it gets evaluated at x comma 0. So you have, so x comma 0, you have the point over there. and then it's just wherever it ends up with. Like, I mean, we do not care what that is, right? I mean, this is just some point in this chart. I mean, that's all it is. What really matters is this is an orientation preserving map. So when you take the determinant, so the determinant of this is going to be equal to the determinant of that. Now, we do not care what the determinant of that is. That's going to be some positive number, because we're assuming we have an oriented atlas, some positive number, multiplied by the determinant of the other one. That should have been that should have been lambda, f lambda inverse composed pi at x0, right? And so what you see is that this is sort of like sigma of x, that's sigma of x, and that's equal to a positive number times sigma of x. So sigma is well defined, right? So sigma is well defined precisely because you're assuming that you have an oriented atlas. Okay, so you have a well-defined map. It does not, if you pick a different chart, it is true. You see, the whole point of the argument here is to show you that if you pick a different chart, it is true that maybe the Jacobian might be different, but the sign of the Jacobian will be consistent. Okay, so I'm going to remove this because otherwise it just gets in the way, but this is the way you would show it, right? This is the way you justify that. So let me just remove this out of the way, and I'm going to just write down the important part. So like to summarize, the main idea of what we're saying is, let's say this. So since the atlas O is oriented, sigma is well defined. It does not depend on what chart you pick, because at the end it comes down to doing some calculation with the Jacobian, and being well defined means that the transition functions between charts have positive Jacobian. Since this involves the sign of the Jacobian, what we've carefully shown is that sigma is a well-defined function. Okay, furthermore, sigma from R to plus minus 1 is a continuous map. So in fact, sigma is locally constant. If it's locally constant, it has to be continuous, right? Constant functions are continuous. And if you're saying something is continuous, it's enough to show that locally on every open set, it is continuous. Well, if on a small open set, it's constant, so that means locally, it's continuous, right? It's constant. So how do you show that this is continuous, or even better, that it's locally constant? Well, it's actually very simple. I'm not going to write this out because I think this is very clear to understand, but let's go back to the definition. So when you go back to the definition, when you pick this point x, and you map it here, you pick a chart that contains it. Well, if the chart contains it, then it also contains all of the neighboring points. So if you pick a point that's very, very close to x, right? If you pick another point, let's call it y, then the y will end up somewhere in the same chart, right? It will end up in the same chart. And you're still using, right? You're still using, right? You're still using the same map, right? If the Jacobian is positive, right? If it's something positive, then it's positive locally, right? If something is positive, then there's an interval on which it is positive. So there's a little room in which you can move around. So if you just slightly move around, it's positive. If the Jacobian is equal to like 5 and you slightly perturb it, then maybe the Jacobian will slightly change and it will become 3 or something, but it will still remain positive. So as long as you make small little perturbations around x, you will be changing the Jacobian by just a little bit, right? But the sign will remain the same, right? So that's the idea, because if you slightly perturb where you're located, you're still in the same chart, right? You're in the same chart, so you're still using the same composition. You're not jumping to a different chart. So that's like the explanation for why this map is continuous. Now you can of course write out a formal proof for that, but it just makes it kind of gets in the way. That's not the main idea of the proof. This is more elementary topology. The other one, the fact that it's well defined is something new. That's why we've carefully written out the proof. But I think this one is clear enough, and you can probably write out the details yourself, that it's a continuous map. So since it's a continuous map, what does that mean? So since but R is path connected, it's a path connected space. So the image sigma of R, right, the image space, right, the image of this has to be a path connected subset, must be path connected also. Subset of 1 and -1. But this is a disconnected path disconnected space, and these are the two components of it. So that would mean that the image is either +1 or -1. So hence, sigma of R is equal to +1 or -1. In other words, i.e., sigma of x is equal to +1 for all x. So it's consistently equal to +1 for all x. Or it's consistently equal to -1 for all x. Right? These are the two options that you can have. And from here, this is how we're going to get the contradiction. So let's go back to this. So now, observe that we have the following relationship. That if you do sigma lambda composed with pi, and you compose that with alpha, that will give you the same thing as this. So why is that? So the reason why that works is because alpha is the automorphism, and pi sends a point into the same equivalence class. So if you just work this out, so like let's say you have f lambda inverse composed with pi, composed with alpha, and then you evaluate all of this at the point x comma y. So what would happen? Well, what would happen is we will have f lambda inverse composed with pi. Well, you will have, so if you just write this out, you would have pi alpha x comma y. But this is x +1 -y. That's how the automorphism was defined. But this is in the same equivalence class. So pi of that, it's in the same equivalence class. So that's why you can just replace that by pi of x comma y. Because x comma y is in the same equivalence class as x +1 -y. So that's the reason why this ends up working out, that we have this relationship, that composing with alpha will return to you the same map again. So what does this imply? So we have, so thus, right, so thus, if we take the derivative of both sides, so we have f lambda inverse composed with pi, and we take the derivative, we're going to, so we have the derivative, and then we have to multiply by the derivative of alpha, and we're going to take a derivative somewhere, so let's take the derivative at our point x, at x comma 0. Right, so we're going to take the derivative at this number x, right, so at x comma 0. So we take a derivative at that point. And then, of course, when we use the chain rule, right, it's a composition. So when we use the chain rule, the derivative will be evaluated at alpha applied to that point. So that would be the point x +1 -0, right? Because that's how alpha is defined, right? Maybe we can go at the very beginning and just see how alpha is defined. So alpha is defined that you take the x and you shift it over by 1, and you take y and then you negate it. So if this is x comma 0, this will become x +1 comma -y. Okay, so we have this result. So we have this relationship, okay, and we're evaluating this at that point, and that's equal to f lambda inverse, and we have a derivative at x comma 0. Okay, now let's compute. So I'm going to keep these the way that they are. Okay. We're going to keep these the way that they are. And let's calculate what this is. So this is going to be a matrix. And this is going to be the matrix. This is a 2 by 2 matrix. And let's work it out. So let's do it right over here. So alpha, it's a map from R2 to R2. Well, technically, it's a map from x to x, but that's not a big deal. And the way it's defined is that alpha of xy is given by x plus 1 negative y. So that's an affine map. If you want to find its derivative, so the derivative of alpha, you would do this. You would take the first component of alpha, and you will calculate the derivative with respect to the first variable. And then you take the first component and you find you differentiate it with respect to the second variable, and then you do it with the second component like this. So if you work it out, the first component is the function x plus 1, and you differentiate it, you get 1, you get 0, 0, negative 1. That's what you end up getting. So the derivative of this map is actually a constant matrix, regardless of what you pick in for the point. So you'll end up with the matrix 1, 0, 0, negative 1. The important part here is to recognize that its determinant is negative. So thus, the sign of the left-hand side is equal to the sign of the right-hand side. But let's calculate the sign of the left-hand side. So the sign of the right-hand side, that is quite simply sigma of x. Sigma of x. Why? Because that's the definition of the sigma function. Right? That's exactly how we define sigma. Just to show you again, this is exactly how we define sigma. You evaluate it at x0, you evaluate it at the belt, right? You evaluate it at the belt. You calculate the derivative at that point, and you take its sign. So the sign that you get, that's just the right-hand side, right? That's just sigma of x. Now, here we have not x, we have x plus 1, right? You see, by using alpha, we have translated something on the belt. So it's still at 0 because that's negative 0, but this is now x plus 1. It's a different point, but it's still in the same chart, because when you go around the belt, right, if you have x and you move it over by x plus 1, it's a different point in x, but on the Mobius band, you kind of go around and you're back there again. So this is the derivative at x plus 1, and so by definition, this is sigma of x plus 1. So that is going to be sigma evaluated at x plus 1. But then you have to be careful that when you take, I should have said it's the sign of the determinant of the left-hand side and the sign of the determinant of the right-hand side. I forgot to say that. So, but this one, its determinant is negative 1. So it's this. So it's, now what's the problem here? Well, you can see what the problem is. So this contradicts. So this is true, right? The above equation contradicts that sigma at x is either plus 1 or equal to negative 1 for all x. That's what we said earlier, that sigma is consistently the same sign. So if sigma is plus 1, then this one has to be plus 1. But then you have a problem that 1 and negative 1. If this is, however, negative 1, then this also has to be negative 1. But then you have a contradiction that you have 1 is equal to negative 1. So you have you have this contradiction that occurs. And you get to see this is x plus 1 and this is x. And that actually is consistent with our intuition of why the Mobius band is not orientable. Because what's the intuition? The intuition is that if we do a full complete revolution, we end up on the other side. But how do we do a full complete revolution? We get the full complete revolution by shifting 1 over. So if we were to shift everything over by 1, right, if we were to shift everything over by 1, as we move from x to x plus 1, we're moving around this belt, but we make 1 complete revolution, and we're back to where we started. But now, mysteriously, we're on the other side. And that's what we're saying, that if we're at some point on the belt and we're on the inside, then by doing a 1 full complete revolution, we're now on the outside, but we're on the other side, right? We're on that point of that -1. But the nice thing about this proof is that it completely makes this entire idea completely rigorous. You get to see the contradiction, right? And hence, we have shown, so thus, O cannot be an oriented atlas. So M has no oriented atlas. That would just mean M is not orientable. So here's a completely rigorous proof for why the Mobius band is not an orientable manifold. I think this is a very nice proof. There's no hand-waving whatsoever. There's no pictures. It's completely rigorous. We're following the definitions. These pictures are just part of the motivation to help you appreciate what we're doing, but you can see, you can remove the pictures and the arguments, they go through just fine. So I think this is a nice proof to actually get to finally see why the Mobius band is not orientable, despite hearing that a lot. Let us finish this long lecture with some concluding remarks. In no particular order. The first one that I want to start with is that the cylinder, so here we'll talk about the open cylinder because we want it to be a manifold, and the open Mobius band. Well, you know what? I'll just draw in the boundary, but we understand the boundary is not included. Are not homeomorphic. And this seems like a very innocent statement, but amazingly, we do not have tools in topology to prove this. Like, you would think that, I mean, it seems like an easy fact to prove, but if you try using some of the standard arguments, like this is path connected, that is path connected, if you remove a point here and you remove a point there, it's path connected. You can try calculating the fundamental group, but the fundamental group of the cylinder can be homotoped to its belt, and the Mobius band can be homotoped to its belt. So the cylinder and the Mobius band, they can be both homotoped to a circle, and so their fundamental groups are the fundamental groups of the circle. And in particular, not just their fundamental groups, but because they both homotope to a circle, it means their homology groups are identical. So if you try using any of the topological invariants that we've talked about, you will not be able to distinguish between these two spaces. But they're not homeomorphic. So how do you prove it? Well, the idea here just comes down to this. Using orientability, you can prove this. What you would say is that the cylinder is orientable. This is orientable, whereas the Mobius band is not orientable. And if you're wondering why orientability is a topological invariant, well, that's actually very simple, because assume there was a homeomorphism. So assume you had a map, let's call it phi. that was a homeomorphism between these two spaces. Then the way you can orient the Mobius band is you choose an oriented atlas for the cylinder, which, I mean, it's very easy to come up with an oriented atlas for a cylinder. So let's say this is let's say this is a chart. Okay, so let's say this is a chart that maps R2 homeomorphically to an open subset of the cylinder. But if you compose it with phi, then you map it, right? Then the composition will give you a chart on the Mobius band. Okay, and then that will give. So if you have an atlas on a cylinder, then that will give you an atlas on the Mobius band, coming from composition with this map. And then the change of coordinates between any two charts would be the change of coordinates coming from over here, because it's just you're using the homeomorphism to transport this over to a different space. So the change of coordinates would be the change of coordinates coming from the atlas for the cylinder, but the change of coordinates between charts has positive Jacobian because the cylinder is orientable. So that would mean you're able to construct a oriented atlas for the Mobius band. So that's why orientability is actually a topological invariant. That's very easy to show. But this is orientable, this is not. So it means that the cylinder and the Mobius band are not homeomorphic spaces. So that's, I think, a pretty interesting proof because it uses something new that we have not talked about. But what's even more amazing, so the amazing part about this proof is that it uses calculus to establish a topological fact. Think about that. Showing that the cylinder and the Mobius band are not homeomorphic, that is a purely topological problem. It has nothing to do with calculus. But to prove it, you use orientability. And orientability is defined for manifolds, and manifolds themselves invoke calculus because you're talking about Jacobians and all of that. So you're using calculus to establish a result in topology, and that's quite amazing. And it goes back to what we were saying, that this is sort of the key idea, that by introducing smoothness, this allows you to solve problems in topology that you otherwise cannot solve. Right? That's kind of like the big idea of all of this. And we've mentioned this before, but I mean the best example of this is the most extreme example of this is the Poincare conjecture. So as we mentioned in class, the Poincare conjecture is for three-dimensional manifolds. Okay, let's say compact, three-dimensional compact manifolds. You assume it's path connected, and then it's a known fact that three-dimensional manifolds can be triangulated, and as a result, it is a smooth manifold. So it has a smooth atlas. Once you make it a smooth manifold, you can do something called geometric analysis on the manifold. Geometric analysis is basically you're doing PDEs on a manifold, but PDEs only make sense when you have smoothness, and you then are interested in something called Ricci flow, which is basically like heat flow, and the geometry of the manifold will influence certain properties, and that's kind of like the way, I mean, an extreme oversimplification of the proof, but those are like the ideas that went into it, and you can see that from this point on, you're just using smoothness from that point on. So you are invoking calculus to establish a result that is purely topological in nature. So the next interesting remark that I wanted to say is I'm going to make a proposition over here that if X is orientable, so whenever we talk about X being orientable, we're of course assuming that X is a smooth manifold. Otherwise, we cannot talk about being orientable. Orientability is in terms of a smooth atlas. It is possible in some cases to define what it means to be orientable in a purely topological way, but let's not even go there. That's more complicated. Usually that's what people mean. So if X is orientable and U is an open subset of X, then you did have a homework problem to show that U itself is a smooth manifold. And furthermore, the inclusion map from U into X, right, the obvious map from U into X, the inclusion map, is a smooth map. But furthermore, not only is U a smooth manifold, but that U is also orientable. Now, I want to just give a warning. I want to give you this is a misapplication of this proposition. This proposition is actually very easy to prove. I'm going to put this on the homework, and you can prove it. It's only a few lines. Maybe some of you already see how to prove this. So there's going to be the incorrect way to use this proposition. So observe that R3 is an orientable manifold. Why is it an orientable manifold? Well, R3 has a very simple atlas. Okay, so to show it's orientable, you have to construct an atlas. And the atlas here is just the identity chart. It's the map that sends R3 into your space R3. And this is a homeomorphism, and its image completely covers R3. So R3 happens to be a smooth manifold with a single chart. I know it sounds silly, but it's still important to carefully check the definitions. And because you only have a single chart, there's nothing to check, right? It's automatically orientable. So R3 is orientable, and the Mobius band M embeds in R3. Okay. I know that previously, when we defined the Mobius band, we defined it abstractly as a quotient space, but you could come up with an embedding, and so you can find a subset of R3 that is homeomorphic to the Mobius band, and that's typically the way we draw it. When we draw the Mobius band, we always draw it as an embedded subset of R3. So M is orientable. Right, that's what you would say. So M is orientable, but we just said M is not orientable. So what is going on? Well, what is going on here is, in the proposition, it's actually important to pick an open subset of your manifold. And the Mobius band is not an open subset of R3, right? It has no thickness to it. So that's why you are misapplying the proposition. So that's just something to be careful about. However, here is an application of this proposition. This is something that you can actually do. We can show that the projective plane is not orientable. Of course, intuitively, it makes sense why the projective plane is not orientable. When we visualize it in some kind of way, we only see one side. But to prove it rigorously, what you would do is you just have to observe that there is an open subset of P2 so that U is homeomorphic to the Mobius band, M. And if you're not sure why that is, well, the way we often represent the projective plane is we draw a disk, and then we say that, so we have this disk, and then the upper circle gets identified with the lower circle in an antipodal fashion. So now look at this. Imagine you draw a band going straight like this. Okay, so we have this entire band, and then this piece gets glued with that piece, but with the opposite, they kind of get glued with a twist. And if you look at the thing in red, that is exactly a Mobius band, right? This is exactly a Mobius band. So the point is that the projective plane, which, by the way, is a smooth manifold, that was a homework question. The projective plane, actually any projective space, is a smooth manifold, but in particular, the projective plane is a smooth manifold. And the question is, does it have an orientable atlas or not, right? An oriented atlas. And if it had an oriented atlas, then it would mean that every open subset of the projective plane will also have an oriented atlas. But here's an example of an open subset. Of course, you would just make these like dashed lines, and that will give you that open Mobius band that we talked about. And that would be an open subset of the projective plane that would have to be orientable, but it is not because it's homeomorphic to the Mobius band. And this is just one copy of the Mobius band. You can also come up with the Mobius band in a different way. You do not have to do it like this. You can kind of twist it like this. That will also work. There's infinitely many versions of Mobius bands sitting inside the projective plane. That's just one way to do it. And this is a nice, satisfying proof why the projective plane is not orientable. And then in a similar way, you can also show why the Klein bottle is not orientable. And so on, because the Klein bottle contains a Mobius band as well. Now, I want to just finish with one last remark. So this is the last concluding remark. So in topology A, if you've never taken topology A, that is okay. But those of you who have, you probably remember this result. So one of the key results of the entire semester, you can say, was the classification of surfaces. And by surfaces, what did we mean? We meant that this was a compact, two-dimensional, path-connected manifold. Okay, so that was the assumptions that we made. So basically two-dimensional manifolds, but you had these extra assumptions. So that's what we mean by a surface here. And we had a classification result. And the classification result was basically the ones are either the sphere, the torus, which I'll just write as T2. This is the two-dimensional torus. And then you have the projective plane. And these are the building blocks. So you can then take the connected sum of two tori. So if you have no idea what this means, then just ignore that. But if you have taken topology A, or you know what I'm talking about, then what I'm about to say will make sense. And then you can take the connected sum of three tori, and so on. And the other thing you can do is you can take two copies of the projective plane. For those of you who might recall, this is the Klein bottle. You can take three copies of the projective plane, and so on. So that was the complete classification of all surfaces. You do not take connected sums with the sphere because the sphere is sort of like an identity for connected sums. And then we said that you call this the orientable surfaces, and you call the other types the non-orientable surfaces. Now, this is what we did in topology A. In topology A, we simply defined orientable versus non-orientable by fiat. So by fiat, I just mean we just declared, right? We had a classification theorem, right? And based on that classification theorem, these are the types that we have. So these types, we call them the orientable types, and those types we call the non-orientable types. So we never really defined what it meant to be orientable and non-orientable. We just kind of split it into two classes, and just by fiat, we just gave a name to both of those classes. And back in topology A, I say that there is a more like a way to actually define orientability as a property. And now that we have done so, so it could be shown, which is not easy, that every surface is a smooth manifold, right? So every topological surface can be given a smooth atlas. That basically comes down to triangulation. If you can triangulate, then you can use the triangulation to create a smooth atlas out of it. So if you're willing to accept that fact, then every surface is a smooth manifold, right? Like the classification theorem tells you how to represent these as polygonal, like polygonal surfaces. Once you have a polygonal surface, then you can use that representation to give it a smooth atlas. So every surface is a smooth manifold, and then you're just talking about whether or not they are orientable or non-orientable. So these are orientable because you can come up with an explicit smooth atlas for these, whereas these are non-orientable because you can show by a very similar argument they all contain Mobius bands as open subsets. So that's why these are the non-orientable ones and those are the orientable ones. So that's, maybe you would find that helpful going back to topology A and thinking about this again. So with that, we have concluded this very long lecture.